My name is Max Strader. Last year I was a senior at Wilson High School. I worked on this project with Ed Gallagher, Stella model on how serotonin in the synapse is affected by selective serotonin reuptake inhibitors. So here's the model. We'll go into it in a second. First we have to do an introduction. Serotonin is a neurotransmitter, which is a chemical that helps transmit messages in the brain between neurons, that helps regulate various emotions, sleep, and hunger. And is also known to be involved with psychological disorders, including obsessive-compulsive disorder, OCD, and major depressive disorder, which is better known as just depression. So how does serotonin transmit a message from neuron to neuron? Well, first, what happens is an action potential, which is an electrical signal, will go down one of the arms of a neuron, called a dendrite, towards a synapse, which is a small, tiny gap between two neurons. When the action potential reaches the end of the dendrite, called the axon, it starts a chemical reaction where serotonin is released from the presynaptic cell at the end of the dendrite into the synapse, the gap between the two neurons. The serotonin then moves across the synapse to the postsynaptic cell, where it binds with serotonin receptors, which then, once enough serotonin is bound to them, restarts the electrical signal and the message is transferred. And after that, the serotonin unbinds from the serotonin receptors, moves again across the synapse to the presynaptic side, where it binds with reuptake transporters, serotonin transporters, which are in charge of a process called reuptake. And what they do is serotonin will bind to these serotonin transporters, which will then move the serotonin back into the presynaptic cell, where it can wait for another action potential to be released into the synapse. Selective serotonin reuptake inhibitors, or SSRIs, are a class of modern antidepressant that works, as the name implies, by inhibiting reuptake, or the process of serotonin moving from within the synapse back into the presynaptic cell. It works by binding to the serotonin transporters that serotonin would bind to undergo reuptake. So there becomes a competition for a limited supply of serotonin transporters. So the more SSRI there is in the synapse, the more it will bind to the serotonin transporter, so serotonin won't be able to undergo reuptake as much, and so it will stay in the synapse longer, and serotonin activity will be increased because then it can go and bind with the serotonin receptors on the postsynaptic cell more and more, and that will increase serotonin activity. So this is our model, and it can be divided into three basic sections. The one on the right, highlighted in red, has stalks representing the amount of serotonin inside the cell and within the synapse. The blue section controls the mechanism for reuptake, the serotonin transporters, and the green section is the mechanism for SSRIs competing with serotonin for serotonin transporters. So the red section, we have two stalks. We have intracellular serotonin, which is serotonin within the presynaptic cell, and then we have extracellular serotonin, which is serotonin within the synapse. So just like in the brain, if we have serotonin within the presynaptic cell, an action potential will come along, and action potentials are created by the converters on the right side of the image, and it releases serotonin from within the cell into the synapse. And that's what this synaptic serotonin release flow does. And then once it's in the synapse, it eventually, through the serotonin transporters, which I will get to in a second, undergoes reuptake and is put back into the presynaptic cell. The serotonin transport, which is the blue section, this actually controls the process of reuptake. So the more serotonin there is within the synapse, or extracellular serotonin, the higher the concentration of serotonin in the synapse is. And that increases the amount of binding between serotonin and serotonin transporters. So in the top left we have a stock called unbound serotonin transporters. The more serotonin there is in the synapse, the more binding will occur between serotonin and serotonin transporters. And so that flow, called serotonin binding, which goes from the left stalk to the right stalk, which is serotonin transporters bound to serotonin, and so it will use up more and more of the serotonin transporters. Then it will, once it's bound to the serotonin transporters, it's undergoing reuptake, it will unbind, and it has then undergone reuptake. The green section is a section for SSRIs. On the top right, again, we have the same stock, unbound serotonin transporters. And that shows how, because there's two flows coming out of it, it shows how there will be a competition for a limited supply of unbound serotonin transporters. And so SSRI does pretty much the same thing as serotonin. It just binds through SSRI binding flow to the unbound serotonin transporters to use them up so that serotonin will stay in the synapse longer, and then eventually unbinds and can continue this process. So here's the full model. Let me walk you through kind of what serotonin does within the model. So starting up here, we have intracellular serotonin. This is the serotonin within the presynaptic cell. Then what happens is serotonin, an action potential comes along, which are controlled by these converters over here. You can adjust the amount of time between action potentials and the interval between them. And it causes serotonin to be released through this flow into the synapse, or extracellular serotonin, which controls the concentration of serotonin in the synapse. And the higher the concentration of serotonin in the synapse, the more serotonin will bind to unbound serotonin transporters up here, up in the middle stalk. And it will become bound to serotonin, and that is when it's undergoing reuptake. Eventually it'll unbind, and the more serotonin binding to serotonin transporters, the more reuptake will occur, which will then, up in the top right stalk, create more intracellular serotonin. However, SSRIs also try and bind to the serotonin transporters in the left section. So the higher the concentration of SSRI, the more SSRI will bind to serotonin transporters, which will lower the amount of unbound serotonin transporters, limiting the amount of serotonin that can bind to them. Now, I talked about it a little bit, but go more explicitly into the feedback loops. There are two main feedback loops in this model. The extracellular loop, which is a counteracting feedback loop, and the intracellular feedback loop, which is a reinforcing feedback loop. So the extracellular feedback loop, which is highlighted in red here, the direction of it, is a counteracting feedback loop. Simply put, it says that the more serotonin there is in the synapse, the more is going to undergo reuptake, which removes serotonin from the synapse. The other feedback loop, the intracellular feedback loop, is reinforcing. And again, simply what it says is the more serotonin in the synapse, the more serotonin will undergo reuptake, which will put more serotonin into the presynaptic cell, and then when an action potential comes along, the more serotonin will be moved back into the synapse. So it's reinforcing. So here we have some model testing. So this is a graph of what happens. This is a graph of serotonin in the synapse, or extracellular serotonin, with one single action potential coming along. Serotonin quickly jumps up as an action potential releases it into the synapse, and then as reuptake occurs, it curves down with exponential decay because of the counteracting feedback loop, and is slowly removed and brought back into the cell. This graph shows what happens when you adjust the interval, when you have multiple action potentials and you adjust the interval between the action potentials. And what it shows is that the smaller the interval is between action potentials, the greater the serotonin level becomes in the synapse. Because what happens is you get serotonin released into the synapse, and then it starts undergoing reuptake. Then you have another action potential, and more serotonin is released, and it starts going down again, and it eventually will reach an equilibrium and just create a flat sawtooth pattern. This is the final product of our model, what we actually wanted to figure out. And what it shows is that as you increase the SSRI concentration in the synapse, there becomes more competition for those serotonin transporters, and so serotonin ends up staying in the synapse longer and longer. So serotonin activity is increased, which is how it works in antidepressants and helps with things like depression and OCD. So here are my references, and I also just really wanted to thank Ed Gallagher for his expert help on the project. Thanks.